Hello everyone, my name is Charan Aditya S. I am working as an assistant professor in Hindustan College of Engineering and Technology in the Department of Food Technology. So today we are going to discuss about the fluid properties and flow characteristics in fluid mechanics. So define fluid. What is a fluid? A fluid or liquid which is capable of flowing and taking any form or shape that is given to it is called a fluid. A fluid is a substance that continually deforms under an applied shear stress. Like liquids are like water, milk, air, and steam. They may be considered as fluids. The matter exists in two states, solids and fluids. Fluid state being commonly divided into liquid and gaseous state. Difference between solids and fluids. A solid is generally the shape and takes its own shape and change in volume under pure compressive load. It is resistance to change in shape without a change in volume under the application of tangential force. The spacing and latitude of motion of molecules are very small in solids, large in liquids and extremely large in gas. So in this solid, liquid and gas, the molecules are larger in gaseous state. The intermolecular bonds are very strong in solids and weak in liquids and very weak in gases. So the intermolecular bonds is weakest in gaseous state. So solid, liquid and gas. Solid is rigid, fixed shape and fixed volume. Liquid is not rigid, no fixed shape and fixed volume. Gas is not rigid, not fixed shape nor fixed volume. This is the difference between solid, liquid and gas. So fluid mechanics. Fluid mechanics is the branch of science which deals with the behavior of fluids, that is liquid or gas, which is at rest or as well as in motion. This branch of science deals with the static, kinetic, kinematics, and dynamic aspects of fluids. The study of fluids at rest is called as fluid statics. The study of fluids in motion where pressure forces are not considered is called fluid kinematics. The pressure forces are also considered, which is in motion. That branches of science is called dynamics. So different types of fluids. Basically, the fluids are classified into five types, and they are ideal fluid, real fluid, Newtonian fluid, non-Newtonian fluid, and ideal plastic fluid. So now we are seeing the graphical representation image of the types of fluids with shear stress as y-axis and velocity gradient as x-axis. So you can see ideal fluid when first one, the ideal fluid, when shear stress increases, the ideal fluid also increases in a straight line, that is along the x-axis. And Newtonian fluid, when shear stress increases and velocity gradient also increases, similarly it travels in motion. So similarly all the fluids contain different properties as mentioned. So let's see about each types of fluids. First one, ideal fluid. A fluid which is incompressed and have no viscosity falls in the category of ideal fluid. Ideal fluid is not found in actual practice, but it is an imaginary fluid because all the fluid that exist in the environment have some viscosity. There is no ideal fluid in reality. So real fluids, a real fluid which has least some viscosity is called real fluid. Actually all the fluids existing or present in the environment are called real fluids. So for example, water is a real fluid. Next is Newtonian fluid. Newtonian fluid, if a real fluid obeys the Newtonian's law of viscosity, that is shear stress is directly proportional to the shear strain, then it is known as Newtonian fluid. Example, water, kerosene. Non-Newtonian fluid, if the real fluid does not obey the Newton's law of viscosity, then it is called as non-Newtonian fluid. Example, paint, toothpaste, etc. So difference between Newtonian and non-Newtonian fluids. The Newtonian fluids which obey the Newton's law is very light and the thickness is very shallow. But in non-Newtonian, as you can see, paint, toothpaste are all thick in consistency. So that is a major difference. Next is ideal plastic fluid. A fluid which is a fluid having the value of shear stress more than the yield value is directly proportional to the shear strain. This is known as ideal plastic fluid. Next is properties of fluids. So in this properties of fluid, the first one is density or mass density, which is represented by the symbol rho. Density or mass density of a fluid is defined as the ratio of the mass of a fluid to its volume, which is given by the formula mass of fluid density equal to mass of fluid by volume of fluid. It is represented in the units kg per meter cube. Next one is specific weight or weight density. Specific weight or weight density of a fluid is the ratio between the weight of a fluid and its volume. The weight per unit volume of a fluid is called specific weight or weight density. It varies from place to place because of acceleration due to gravity changing from place to place. The specific weight is represented by weight of fluid divided by volume of fluid, and its units are Newton per meter cube. Next one is specific volume. Specific volume of a fluid is defined as the volume of a fluid occupied by a unit mass or volume per unit mass of a fluid. The specific volume is represented by the symbol small v equal to volume of fluid by mass of fluid. Its unit is given in meter cube per kg. Next is specific gravity or relative density. Specific gravity is defined as the ratio of the density of a fluid to density of a standard fluid. That is S equal to density of a fluid divided by density of a standard fluid. The standard fluid can be used, the water can be used as a standard fluid. The specific gravity of mercury is 13.6. It is an universal value. Next is viscosity. Viscosity is the property of a fluid due to cohesion and interaction between molecules which offers resistance to shear deformation. Different fluids deform at different rates under the same shear stress. Fluid with a high viscosity such as syrup deforms more slowly than fluids with a low viscosity such as water. So shear stress is represented by the symbol tau equal to mu into du by dy. Next is dynamic viscosity. It's defined as the shear stress tau required causing unit rate of shear deformation. That is mu equal to tau divided by du by dt. Its unit is represented in Newton per second per meter square. Then kinematic viscosity. It is defined as a ratio of dynamic viscosity to mass density, which is V equal to mu by rho. Its unit is meter square per second or stroke. Next we are going to see about the vapor pressure. So vaporization, a change from liquid state to the gaseous state is known as vaporization. Vapor pressure is the liquid is kept in a closed vessel. The vaporization takes place and the molecule escapes from the free surface of the liquid. This vapor molecules occupy the space between free liquid surface and the top of the vessel. So you can understand between the uh, between the between the top of the vessel and the liquid surface, the space in between is the where the gas produces these accumulated vapors. I mean, the vapor produces these accumulated vapors exert a pressure on the liquid surface. This pressure is called the vapor pressure of the liquid. Vapor pressure of water is 233.7 Newton per meter square at 20 degrees Celsius. Next is surface tension. Surface tension is defined as the tensile force acting on the surface of a liquid in contact with the gas or on the surface between two immiscible liquids. Immiscibles in the sense liquid and water cannot be mixed uh, cannot be mixed naturally. So we should mix using a pressure or force that is called as immiscible liquids, such as the content surface behaves like a membrane under tension. Due to molecule attraction, liquids have properties of cohesiveness and adhesiveness. The cohesiveness is due to the force of attraction between molecular of same liquid. This force is very small. Adhesiveness is due to the force of attraction between the molecules of two different liquids. This molecule of the liquid and molecules of solid surface. So this is an image representation. Next is capillary rise. If the gas tube is inserted vertically in a liquid, say water, the liquid will rise in the tube above the level of liquid surface is known as capillary rise. Then capillary depression or capillary fall. If the gas tube is dipped vertically in a liquid, say mercury, the level of mercury in the tube will be lower than the general level of the outside liquid. These the two forces acting on the mercury inside the tube. First one is due to surface tension acting in the downward direction. And the second one is due to hydrostatic force acting upward, and is equal to the intensity of pressure at a depth. Next is applications of Bernoullis equation. So in Bernoullis equation, the Bernoullis equation consists of these following meters: Venturi meters, orifice meter, pitot tube. In these three meters, I mean these three equipments, the principle followed is Bernoullis equation. So this is an image representation of Venturi meter. This is an orifice meter. So other details we'll be seeing on the next video. Thank you for listening. Hope you understand.